In this second segment, we'll start with the proposition 3, which states that every compact subset K of a Hausdorff topological space S is closed. Okay. So let's prove it. So we're going to use a result to prove this proposition that I'm going to state without proving that. That I'm going to state that important result without proving it. The proof utilizes the result. The proof utilizes the result that a compact subset K in a Hausdorff space S can be separated from a point P not in K by disjoint open sets. By disjoint open sets. That is, there exists an open set U containing K and an open set V containing P, the point, such that the intersection of U and V is empty. Okay, so let me give you a picture for understanding it a little more clearly. So say that we have a compact subset K in the topological space S, and there is a point P which is not in K. Okay, so we'll always be able to separate P from K in the sense that we can draw open subset containing K and another open subset containing P, such that these two open subsets doesn't have any point in common. Okay, so we can always separate this point P from K. So this is the result. Okay. So according to this result above, the one that we have mentioned here, for every point P in S set minus K, okay, which means that P is not in K and P is in S, one can find open set V containing P such that V is contained in S set minus K. Okay, which means that V is not intersecting K. All right. So for each point P in this set, we'll be able to find an open set V containing V such that this open set is entirely contained in S set minus K. It follows from this separation result. What does it mean? It means that S set minus K is open, right, in S. So if S set minus K is open in S, it means that K is closed in S. Okay, so this proves the statement of the proposition 3, QED. Okay, so our next proposition is about the image of a compact set under a continuous map being compact. Okay. So let's prove it. Let me first state proposition 4, which states that the image of a compact set under a continuous map is compact. Proof. Okay. Good. So let f from x to y be continuous, and k contained in x is compact. Okay, right. Now what do we need to prove? We need to prove that f of k is f of k is compact in y, right? So we take an open cover of fk in y and then show that that cover has a finite subcover. That way prove that fk is indeed compact in y. So let's take u alpha to be an open cover of fk in y, okay? Which means that the open sets are all from y, okay, which cover fk, this open sets. So since f is continuous, right, so the inverse image of every open set u alpha in y is also open in x, right? So this guy is open in x for all alpha in some index at I. So moreover, okay, by the way, when we say that this is an open cover of fk in y, we mean that it means that fk is contained in the union of all these open sets, right? So we have this is well known from elementary set theory again, that K is contained in, for any map F, this will always be a containment, okay, at least a strict containment, not an equality for any map, which follows from elementary set theory. And since this, what are we doing? So these are not big F. This is small f. This is small f. This is also small f. Okay. Sorry to write it as big F. There, no big F is here. All small f. Okay. So and since this holds, then taking inverse image on both sides, we have this, the one that I am writing now. Inverse image of this union under F. Okay. And this is by elementary set theory again. This is the union of all these pre-images. Okay, so we have seen that K is contained in this union, right? Which means that this collection of open sets in X is a cover of K, is an open cover, is an open cover of K in X, right? Okay, now by using proposition 2, and the fact that K is compact in X, okay, we immediately see that there is a finite subcollection here for which K is contained in the finite union of that subcollection. So let me write down the finite subcollection here. From I to n, from 1 to n. Okay. So K is contained in this finite union, which follows from the compactness of K. Right. So I need space. I need to erase something to create space for me. And so from here, we immediately see that K is contained in this union, which I am rewriting here, and which is equal to, from elementary set theory again, the inverse image of this union. Okay, and again, then Fk why am I writing it like this? Why is it an equality? That is something that I made a mistake here. That has to be a containment, not an equality. So since this holds, K is contained in this, then F is contained in F of this pre-image thing. Okay. Alpha I. Good. And again, by elementary set theory, no matter what f is, this containment will always follow. Okay. So that is Fk is contained in this finite union. So, okay. So we had earlier Fk. So we started with Fk being a subset. Contained in this arbitrary union, so that U alpha, the collection U alpha was an open cover of Fk. Now we have found a finite subcover of this cover, which means that Fk is compact. Fk is compact. Okay. Good. Q video. Alright, so now our next proposition states that proposition 5, a continuous map f from x to y, where x is compact and y is Hausdorff, okay, from a compact space x to a Hausdorff space y, y is a closed map. For those who are not familiar with the definition of closed map, it's just a map that takes closed sets to closed sets. A map that takes closed sets to closed sets. So all we have to prove is that if we take a closed set from X, then the image of that closed set under F will also be closed in Y. Then we are done proving that F is a closed map. Okay, here is the proof. Again, we'll need a result here that we'll also prove during this proof. Okay, so let F be a closed set of the compact space X, of the compact space X. Now we need the following result. Now we need the following result. A closed subset F of a compact topological space S is compact. Okay. So if we have a closed subset F of this compact topological space S, then F is going to be compact as well. So here is the proof of this result. It's a proof inside proof. Okay. so we need to prove that F is compact, right? So we take an open cover of F and then show that it has a finite subcover. That way we prove that F is a compact set. A compact space, a compact topological space. So let me take U alpha to be an open cover of F in S. The compactness of, okay, then you see that U alpha, comma, the collection of these two open sets, not these two, the collection of all these open sets, okay, so there are many open sets here. You take all those open sets and attach this new open set, S set minus F, which is of course open in S, okay. Then this is going to cover the whole topological space S, okay, open cover of S. So by the compactness of S, there is a finite subcover, right? And let us take that finite subcover to be this finite collection from I from 1 to n is the finite subcover of S. Okay, so it means that S is contained in the union of all the sets. U alpha I union S set minus F. Okay. And you know that F is a closed subset of S, so that F is contained in S. Okay, so it implies that F is contained in this union, right? In this finite union. Okay, now important thing to note is that F is not contained here, right? Because this is S set minus F. But F is contained in this union, so F must be here. F must be here. So we took an open cover U alpha of F in S, and we ended up with a finite subcover of F of this cover in S, which proves that F is compact. Okay, so this is a proof of this result. Now I'm going to erase this part, this secondary result that we need for our proof. Okay. Now we have found that F is compact, right? F is a closed subset of the compact space. We have chosen F to be a closed subset of X, and since X is compact, F being a closed subset of X is also compact by the previous result. F is compact. Okay. Now by proposition 4, since F is a continuous map from X to Y and big F is compact in X, by proposition 4, F of big F is compact in Y, right? Now by proposition 3, which states that every compact subset of a Hausdorff space is closed. So since Y is Hausdorff by assumption, then the compact set F of big F in Y has to be closed. Hence, F of F is closed in Y by proposition 3. What does it mean? It means that this F is a closed map, okay, which we needed to prove. So at the final stage, we are using the Hausdorffness of this topological space Y to prove that this compact set is indeed a closed set. Okay, good. Now there is a corollary to this proposition, which states that corollary to proposition 5. I think I need more space. Let me erase everything. So corollary to proposition 5 it states that a continuous bijection F from X to Y, where X is a compact space, from a compact space X to a Hausdorff space Y is a homeomorphism. Okay. So if you have a continuous bijection from a compact space to a Hausdorff space, that continuous bijection is also a homeomorphism. Okay. So here we have everything except for the fact that the inverse is continuous, right? So in order to prove that it's a homeomorphism, we just have to prove that the inverse map here corresponding to this bijection is continuous. Okay, so let's prove it. So we want to show that the inverse map from the Hausdorff space Y to the compact space X is continuous. Show. Then we'll be done. Okay, so we know that for a continuous map, for a continuous map, the inverse image of closed set is a closed set. Also, if we can prove that for every closed set, the inverse image is a closed set, then we end up proving that the underlying map is a continuous map. that we discussed in the first lecture. Okay, so it suffices to show that for every closed set F in X, closed set F in X, we need to show that the inverse image of F inverse, the inverse image of big F under F inverse, which is nothing but actually the image of big F under F, okay, is closed in Y. So then we will be able to prove that this function is continuous, okay? So then what are you looking forward to? You're looking forward to the fact that the image of every closed set in X is closed in Y, right? Which means that we are looking forward to proving that this small f is a closed map. Okay. So if we prove that this small f is a closed map, then we are done proving that small f is a homeomorphism. Okay. So, but this is the case. This is a closed map by proposition 5, right? Because F is a continuous map from a compact space to a Hausdorff space. So, the image of every closed set in X is also closed in Y, since we know from proposition 5 that F is a closed map. So we done proving that F is a homeomorphism. Okay? Good. Okay, so closing. So this is what we want to prove. So in other words, it suffices to show that F is a closed map, right? But this is the case from which follows from proposition 5. Proposition 5. QED. Good. Now we move to the concept of boundedness in the Euclidean space R to the n. Okay. The concept of boundedness in R to the n. Okay. So a subset A of R to the n is said to be bounded if it is contained in some open ball B centered at P and of radius R. Otherwise, it is unbounded. Okay, so there is an important theorem that I'm going to state without proof now, which is called the Heine-Borel theorem. Heine-Borel theorem. A very important result from analysis. Okay, a subset of R to the n is compact. This only holds for Euclidean space, remember, okay? So a subset of R to the n is compact if and only if it is closed and bounded. Okay, for example, in the real line, okay, in the real line 0, 1, this closed interval is bounded and it is closed, and hence we conclude that this interval 0, 1 is compact. Okay, so it holds for any Euclidean space R to the n. Okay. Okay. So now we get back to our discussion on quotient topology. Okay. So we had enough topological background. Now get back to our discussion on quotient topology that we were discussing. Now back to our discussion on quotient topology. Okay, now I'll give you an example. Okay, example. So identification of a subspace to a point. That's what we were discussing in the quotient topology section, and then we move to this topological background materials and compactness. So let I be the closed interval 0, 1. Okay, in the standard topology of R. Okay, and this is I, and the quotient space is obtained from I by identifying these 2 points. Right? So you are collapsing these 2 points on 0, 1 to a single point in the quotient space. Okay, so this is how you obtain this quotient space. Okay, and so then we denote by S1 the unit circle in the complex plane. Right? Okay, now we have a function f from I to the unit circle S1 in the complex plane C. Okay, S1, the unit circle in the complex plane C. Okay, so how we are defining this function? This function is defined by f of x is equal to e to the 2 pi I x. Okay. So it is easy to see that it's continuous. I leave it with you. Okay, it's a continuous function from I to S1. Okay. And you can see it in terms of components and all that we have done earlier. So in addition to it, it's important to note from this expression of the function that this function assumes the same value at the two endpoints, 0 and 1. But 0 and 1 belong to the same equivalence class under this equivalence relation, right? Because under this equivalence relation, we have identified these two endpoints. This is how we define this equivalence relation. Okay. And which means that this function f is constant on each equivalence class, right? So we have fulfilled all the criteria required for proposition 1. F is a continuous function from I to S1. F is constant on each equivalence classes here. Therefore, the induced function F bar from I quotiented out by twiddle to S1 is also continuous. Okay. So let me draw the picture. This is the unit interval 0 to 1, and this is the function f that carries this this closed interval to this circle S1, right? This is I, and the caption of the figure is the expression of the function, right? So these 2 points are identified here. Okay, so now I have a proposition which tells us that this function f bar, proposition 6, tells us that this function f bar from this quotient space to S1 is a homeomorphism. Okay? Alright, so now I prove it. Okay, so I need space. Let me erase everything except for the statement of the proposition. Proof of this proposition 6. So I leave it with you to prove that this function from I to S1 is indeed a continuous function. Okay. Is continuous. Continuous. Check. Therefore, by proposition 1, we know that this function f bar from the quotient space to S1 is also continuous. By prop 1. Also, note that I equal to this closed interval in R is closed and bounded, and hence by Heine-Borel theorem, I is compact. Okay. Okay. Now, since see that this projection map, the canonical projection map from I to this quotient space, right, is continuous, right? We know that is continuous. Okay. And I is compact, right? And this is surjective, clearly, and the image of I under pi is compact by proposition 4, because this is a continuous map. I is compact, so pi of I, which is equal to this quotient space, is compact by proposition 4. Okay. Now it should also be obvious, right? Intuitively, it's even more obvious that f bar from this quotient space to S1 is a bijection. Okay. So there was only one trouble from of this function for not being injective, because by the definition of the function, at the two endpoints, the function assumes the same value. Okay, so it's not injective, but we identified those 2 points. So the resulting function f bar is bijection by construction. Okay, so it's a bijection. And also, another important thing to see is that this unit circle S1 being a subspace of a Hausdorff space, either C or R2, is again Hausdorff. So any subspace of a Hausdorff space is also Hausdorff. So S1 is Hausdorff. So we have seen that this is compact, this is Hausdorff, right? This is a continuous bijection from a compact space to a Hausdorff space. Therefore, by proposition 5, f bar from this compact space to the Hausdorff space S1 is a homeomorphism. QD. Okay. Good. Okay, now we discussed the necessary condition for a Hausdorff quotient. So so here is the thing. In general, in general, even if S is Hausdorff, under any equivalence relation, twiddle on S, the quotient space, right, is not Hausdorff, is not necessarily Hausdorff. So now we will state the necessary condition for this quotient space to be Hausdorff. Okay, so let me state it by a proposition. Proposition 7. If is the necessary condition, so we assume that the quotient space is Hausdorff. Okay, if the quotient space S modded out by twiddle is Hausdorff, then the equivalence class P containing P of any point P in S is closed in S. Okay, so here remember the abuse of notation I have discussed earlier. Okay, so this at the same time designates a point in the quotient space and also a set in the original space S. Okay, so and this has to be closed in S. Okay, so by this we mean the set of all elements in S that are equivalent to each other. Okay, and that set has to be closed in S. That's what the proposition states. Okay, so let's prove it. Proof. So we know it from the first lecture that every one-point set is closed in a Hausdorff topological space. Okay, so if you have a singleton set, that is going to be closed in a Hausdorff topological space. Now consider the canonical projection map pi from S to the quotient space. Okay. So for a point P in S, this guy is a singleton. Okay. From the well-definedness of this projection map, this is a one-point set, in the quotient space, right? So by hypothesis, since this space is Hausdorff, we have assumed the quotient space to be Hausdorff. Okay. This one-point set has to be closed in the quotient space, right? This must be closed in the quotient space in quotient topology. Quotient topology. Okay. So we have seen that this one-point set is going to be closed in this quotient space in quotient topology. Now, by continuity of pi, this is a continuous map. Okay. So the pre-image of this closed set is going to be closed in S, right? So by continuity, the free image of this closed set pi of p is closed in S. Okay. Well, but what is this? This is nothing but the equivalence class containing P, right? So we have just proved that this equivalence class containing P is closed in S. Okay. QED. Okay, now there is a short remark about the usefulness of this proposition 7. Okay. Remark. So how can we use it? In order to prove that a quotient space is not Hausdorff, it will be sufficient to prove that the equivalence class of some point P in S is not closed in S. So if you can show that there exists a point P in S for which the equivalence class is not closed in S, we are done proving that the quotient space is not Hausdorff. Okay. So this is the usefulness of this proposition 7. So we just use the contrapositivity of the statement in proposition 7 to prove that some space is not Hausdorff, some quotient space is not Hausdorff. Okay. So this is the useful part of this proposition. So using this remark, we are going to see a useful example. Example. So define an equivalence relation twiddle on R. How? By identifying, so this is the real line R, but you are identifying this open set 0 to infinity to a point, and this is how you are defining this equivalence relation twiddle on R. So identifying a subspace to a point. So in this definition of twiddle, 0, infinity is a point, right? So now I'm asking about the Hausdorffness of this quotient space, right? And we immediately see that this quotient space is not Hausdorff. Why? Because 0, infinity, this equivalence class of twiddle in R is not closed. Okay, so we have found an equivalence class in R which is not closed. which confirms that the underlying quotient space is not Hausdorff. Okay. Alright, now a very important concept for our construction of real projective space called open equivalence relations. Okay, let me go over the definition first and then I'll prove some results concerning this definition. Okay, so let me erase everything and then define open equivalence relations. Open equivalence relations. Okay, so we have a topological space and we have an equivalence relation twiddle on S. This equivalence relation twiddle on S is said to be open if the underlying projection map pi from S to the quotient space is open. Okay. So what is an open map? It maps open sets to open sets, which means that for every open set U in S, pi of U will be open in this quotient space. And then we'll say that the underlying equivalence relation is an open equivalence relation. Okay, so so in order to have a feeling of what's going on around, let's have a diagram of say this whole topological space as, and we are going to partition this the topological space by equivalence classes, right? So I'm just following my notes. C, D, and F. Okay. So I am choosing an open set here containing B, C, and D only. Okay. All right. So these are the equivalence classes that we have. Okay, so there are 1, 2, 3, 4, 5, 6 equivalence classes. Okay, and we are choosing representatives from these equivalence classes. Okay, so that they represent the respective equivalence classes, and so you see that the open set is entirely contained in these 3 equivalence classes, right? In these 3 equivalence classes. And now, under the projection map, these equivalence classes are just points, right? One point is E, one point is A, one point is B, one point is C, one point is D, and one point is F. So there are 6 points. So S, this quotient space is nothing but just 6 points. And what is pi U? Pi U is an open set may not be exact what we are doing, but just to have a feeling of what we are doing, this is something like pi u, which contains these 3 points, right? An open set, right? Okay, so now what is the pre-image of this pi u? That I am asking. The pre-image of pi u. Right? So the pre-image of pi u means all the points here in S such that the image of those points under pi will be here. Okay. So if I pick a point from here which is outside of U but belongs to one of the equivalence classes that has overlap, non-zero overlap with this open set that we started with, this open set U. Okay. Then its image will be in pi u, right? Because this is projected to B, and hence we see that the pre-image of pi u in S is even bigger than u, right? And indeed, this is the case. U is contained in this, so this guy, this shaded region, is the inverse image of pi u actually, right? This shaded region, yeah, which is nothing but this is equal to the union of these 3 equivalence classes, right? Which can be written down as x in U and the union of all this x, the class of x, such that each x for all the x's belonging to U, over which we are taking the union. Okay, so this kind of gives you the picture of what's happening around. Okay, so this is a strict containment which is clear from this picture. Okay, they are not equal. So the caption of this figure is, indeed, U is contained in the pre-image of pi U under pi. Okay. Okay, good. So what have you seen? We have seen that for the open equivalence relation, we want the projection map to be open, which is the very definition of open equivalence relation. Okay, and so in other words, the equivalence relation total on S is open. So let me write it here. In other words, the equivalence relation twiddle on S is open if and only if for every open set U in S, the set pi U in the quotient space is open, or from the definition of quotient topology, quotient topology, if and only if, so when is this guy open in this quotient space? If and only if the pre-image of this guy is open, okay, so the pre-image of pi u is nothing, which we have seen in this figure earlier, is the union of all this equivalence classes, right, where x is in U, okay, is open in S. All right. In other words, we want this shaded region to be open in S, which is a very restrictive case. It is always not the situation for any relation, okay, for any equivalence relation. So we have to understand it that many times we don't have the equivalence relation to be not to be an open equivalence relation. Okay. So that was the definition. Now I give you an example of something which is not an open equivalence relation. Okay. So let me erase everything and give you the example. So it gives us the concept that that the quotient space in general, the projection map onto a quotient space in general is not open. Okay. So for example, the equivalence relation twiddle on the real line R, twiddle on R is say defined by identifying 2 points, -1, 1, and then -2. Okay. So so it identifies these 2 points, -1 and 1. Okay. So that's the equivalence relation twiddle. Okay. So this set -1, 1 is identified to a point on R, and that's the equivalence relation. So and this is the underlying projection map. So in terms of a diagram, you see that this guy is going to look like a lace, something like a lace. Okay. And because -1 and 1, they are identified, they're this point. Okay. And we see that the map pi here, if this map is open, I mean that this map pi is open if and only if, so we take an open set from here, okay, from this real line. pi is open if and only if for every open set V in R. From here, pi V is open in the quotient space. Then we said that this projection map pi is open, or in other words, this equivalence relation is an open equivalence relation. So this requirement in turn reduces by the definition of quotient topology to this guy being open in R, right? So if pi v is open in this quotient space, if and only if this is open in R, right? This follows from the which by definition of quotient topology means that this guy is open in R. Okay. All right. So it is going to happen. It has to happen for every open set V in R. Okay. We are going to find an open set for which it is not the case. Then it will prove that the underlying equivalence relation is not an open equivalence relation. So we are going to choose -2, 0 in R, this open interval from R. Then we immediately see that the pre-image of pi V, so this is our V, -2, 0, is going to be equal to -2, 0 union. There is a new point, isolated point 1, isolated from this interval, 1. Okay, why? Because we see that pi of 1 belongs to pi of V. Pi of V is this segment here, right? And 1 is by twiddle, 1 is mapped here. 1 is projected in the same point as -1, right? So what does it mean? It means that pi under this projection is inside pi of V, right? Pi of V. So of course this pre-image is the union of -2, 0 and the singleton set 1. Okay, and this is not open in R. Which means that pi is not an open map, and hence twiddle is not an open equivalence relation. Okay. All right, I think I'll take a break here.